Here's what you've probably heard. A programmer made a mistake, a typo, a bug, one careless line of code, and a rocket blew up. But that's not what happened. The code was perfect. It had been perfect for years. Hundreds of launches. 0 failures. The code didn't fail. We failed the code. On June 4th, 1996, a number became too large. Not large, like a million. Just 33,000. A number slightly too big for the tiny box it was stored in. And in 37 seconds, 37 Zeveler is $10 That's the end of this story. Seconds $307 differed into a fireball over the jungle. By the end of this story, you'll never look at reused code the same way again. When 99087 Europe has a problem. If you want to launch a satellite, you call America. Or you call Russia. There's no European option. Your scientific missions, your communication satellites, your military payloads, they all ride on someone else's rocket. So 12 countries sit down and make a decision. We're building our own. They call it Ariane 5. Not an upgrade. Not a modification. A completely new rocket, designed from scratch. The most ambitious engineering project Europe has ever attempted. 100 companies, 6,000 engineers, 12 countries, and a budget that will eventually reach $7 billion. For context, that's more than the GDP of some of those countries' smaller cities. But there's a reason for the ambition. Ariane 4, the previous generation, was a legend. Over 100 successful launches. Rock solid, reliable. The gold standard. And Ariane 5. Ariane 5 was going to be even better. Bigger payload, better trajectory. Europe's ticket to space independence. For 10 years they build, and on June 4th, 1996, everything is ready. But here's the detail that changes everything. And it has nothing to do with the rocket itself. Deep inside Ariane 5, there's a component called the SRI, the Inertial Reference System. It's the rocket's sense of balance. It tells the flight computer where the rocket is, how fast it's moving, and which way is up. The SRI runs software, and that software was written in Ada, a language literally designed for military and aerospace systems. Safety-critical code. Now, here's where the story turns. When engineers built the SRI for Ariane 5, they didn't write new software. They reused the code from Ariane 4. Why wouldn't they? That code had flown over 100 missions without a single failure. Inside that code, there's an alignment function. It calibrates the navigation platform before launch. It runs for about 50 seconds, and it was critical for Ariane 4. If there was a countdown hold, this function let the rocket restart quickly, without a 45-minute recalibration. For Ariane 5, this function was completely unnecessary after liftoff. Useless. Dead code that nobody removed. But someone had been careful. Sort of. The engineers who wrote this alignment function had identified 7 variables that could overflow. Numbers that might get too big for their containers. They analyzed all 7, and they protected 4 of them with exception handling. 4 out of 7. They left 3 unprotected. Why? Because the SRI computer had an 80% CPU workload limit. Adding protection to all 7 would exceed that limit. So they did the math on the 3 remaining variables and concluded, based on the physical limits of Ariane 4's trajectory, these values can never get that large. And they were right. For Ariane 4, June 4th, 1996, 12:34 UTC, Kourou, French Guiana. The air is thick and humid. Tropical birds scatter as the engines ignite. Thousands of people, engineers, politicians, press, scientists, are watching the culmination of a decade's work. In the payload bay, 4 cluster satellites sit waiting. Each one weighs 1,200 kilograms. Each one represents years of work by space scientists across Europe. Together, they'll fly in a tetrahedral formation to study Earth's magnetosphere, a first-of-its-kind mission. The countdown hits 0. The Vulcain main engine roars to life. The solid boosters ignite. Ariane 5 lifts off. If you've ever watched a rocket launch, you know that feeling. The sheer power. the slow climb that turns into a sprint toward the sky. For the first 37 seconds, everything is perfect. If you subscribe, do it now, because what happens next will haunt every engineer who hears this story. The Asari alignment function is still running. Remember, it was designed to run for 50 seconds after initialization. It started 3 seconds before liftoff. So, it's still counting, still calculating, still converting numbers. And Ariane 5 is flying a steeper trajectory than Ariane 4 ever did, moving faster horizontally than Ariane 4 ever could. Inside the Asari, a variable called BH, horizontal bias, is climbing. T plus 36.7 seconds. The BH value hits a number that Ariane 4 could never reach. The code tries to convert it from a 64-bit floating point number into a 16-bit signed integer. The maximum value a 16-bit signed integer can hold? 32,767. The number is larger than 32,767. Operand error. The Ada runtime detects it, and the specification says, on any exception, shut down the processor. So, the Asari shuts down. But wait, there's a backup. Ariane 5 has 2 Asari units. Redundant. If one fails, the other takes over. Except, the backup is running the exact same software, the same alignment function, the same unprotected variable. 72 milliseconds later, the backup Asari shuts down too, both dead, within the blink of an eye. Now the onboard computer has a problem. The Asari isn't sending navigation data anymore. It's sending a diagnostic bit pattern, basically error codes. But the flight computer doesn't know that. It reads the diagnostic data as if it were real navigation data. And it follows orders. The computer commands full nozzle deflection. The solid boosters swing hard. The rocket turns 20 degrees off course. At that speed, 20 degrees is a death sentence. T plus 39 seconds. The aerodynamic forces rip the boosters off the main stage. The self-destruct system activates. T plus 40 seconds. 3.7 kilometers above the French Guiana jungle. 370 million turns into a fireball. 4 cluster satellites. 10 years of work. $7 billion of development. Gone. In 37 seconds, the jungle smelled like burning metal and rocket fuel. Nearly 100 personnel, engineers, firefighters, security staff, fanned out across mangrove swamps and savanna. Helicopters overhead. Amphibious vehicles pushing through mud. They were looking for one thing, the Asari units. They found them. 9 days after the explosion, Professor Jacques-Louis Lyons, a distinguished French mathematician, sat down with 5 colleagues to answer one question. What happened? They had the Asari hardware. They had the source code. And the answer, when they found it, was almost unbearable in its simplicity. One unprotected variable, in a function that served no purpose after liftoff, in code that was never retested for Ariane 5's trajectory. The inquiry board's conclusion was devastating. There is no evidence that any trajectory data were used to analyze the behavior of the unprotected variables. Nobody checked. Nobody asked, does this code still work in a different rocket? And here's the cruelest detail. The alignment function was designed to run for 50 seconds. The crash happened. The inquiry board didn't blame one person. They identified 5 groups who could have prevented this. The programmers, who could have protected all 7 variables instead of 4. The designers, who could have built the system to degrade gracefully instead of shutting down. The requirement engineers, who could have revalidated the SRI specs for Ariane 5's different trajectory. The test engineers, who could have run a full simulation with actual Ariane 5 flight data instead of simulated SRI output. The project managers, who could have mandated independent code review for all reused components. Any one of them could have stopped it. None of them did, because everyone assumed someone else had already checked. The programmers trusted the specs. The designers trusted the code. The testers trusted the simulations. The managers trusted the process. Trust all the way down. And nobody asked the one question that mattered. Does this still hold true? Think about that for a second. The most expensive software bug in history wasn't a bug at all. It was correct code in the wrong context. Written by competent engineers. Analyzed properly. Tested thoroughly for a different rocket. How many times have you copied code from one project to another? How many dependencies does your current project have? How many of them carry assumptions you've never questioned? In 1996, one unprotected variable destroyed 370 million. In 2020, one unprotected variable destroyed 370 million. In 2026, we reuse more code than ever. Every NPM install, every pip package, every AI-generated function. Each one carries assumptions baked in by someone who never imagined your context. The most dangerous code isn't the code that's wrong. It's the code that's right. For a different world. Ariane 5 flew again. ESA implemented 40 corrective actions. Created the role of software architect, rewrote the rules for code reuse across all European space programs. But it took 11 years, until 2007, before Ariane 5 earned back the trust that Ariane 4 had built over 100 flights, 7 variables, 4 protected, 3 exposed, and 1 that changed aerospace engineering forever. Now, imagine a different kind of trust. It's November 1, 1988. A 23-year-old sits in a computer lab at MIT. He's not an MIT student. He's at Cornell. He's hiding. He's just released 99 lines of code onto a network of 60,000 computers. A harmless experiment to count how many machines are connected. But there's a bug in his code. And that bug has a bug. By morning, 10% of the entire internet is dead. His father works at the NSA, and the FBI is about to knock on his door. Title suggestions. 5 options. 1. The code that was perfect, until it wasn't. Ariane 5. 2. 370 million rocket.